All right, here we are for vector application. So you can be following along with your handout. The first one says a child pulls a sled along level ground by exerting a force of 30 pounds on a handle that makes an angle of 45 degrees. Express the vector in terms of I and J. So here really we're just trying to take the information and create a vector. I think it's super important to always make a picture. So pulling a sled on level ground, so there's our level ground. The handle makes a 45-degree angle. So here's my 45-degree angle. And the force is 30 pounds. So remember when we talk about the force on a vector, that is the magnitude. So in our drawing, we look at that as the length of the vector. So now we want to write this in terms of I and J. So we have a formula that says, okay, if I have a vector, I can do the magnitude of the vector times cosine of the angle. That's my I component, plus the magnitude of the vector times sine of the angle, and that's my J component. Another way to think about that, you don't have to use that formula if you don't want to. If you find that confusing, here's all you need to remember. What are you looking for? You are looking for this to be your AI and this to be the BJ. This is a 90-degree angle. So if you could think of that, then you can say, okay, I have the angle opposite hypotenuse, adjacent hypotenuse. You can just use your trig functions and then write it as a vector. It's really whatever works the best for you. So for my vector V, that means plugging in my actual magnitude, which is the 30, cosine of my angle, which is 45. That's going to be my I component. 30 sine of 45 is going to be my J component. We do exact values whenever we can. So here I can do a root 2 over 2 for both of these. So I get that my vector is, that looks sloppy, I'm sorry, 15 root 2I plus 15 root 2J. And that's it. So all we were trying to get was the vector so that we could do things with it if we need to. So that's, one of the big ideas is trying to create the equation of a vector. Now they are my exact values. When you go to do operations, so you're adding two vectors together to get the resultant, you'll need to go to decimals. But if you're not doing that, then you leave it in its exact value form. All right, so our second problem here is talking about a barrel. Find the magnitude of the force required to keep a 280-pound barrel from sliding down a ramp inclined at 12.5 degrees from the horizontal. Find the magnitude of the force of the barrel against the ramp. All right, so again, picture is going to be super important. So let's have our horizontal. 12.5 degrees is a pretty skinny angle. That's not 12.5, but we're gonna roll with it. Right? We have a barrel. Right? There's my barrel that's resting on the ramp. Right? We know that this is our 12.5. So that's the angle. And it says find the magnitude of the force required to keep it from sliding down the ramp. So what it's saying is that you're here. You're this little person here. And we're saying, how hard do you have to pull against that barrel to keep it from sliding? That's what you're trying to figure out. Okay. So there are a couple of things going on here. We have the actual weight of the barrel. So the weight of the barrel, we have to think of as going straight down because weight deals with gravity. So straight down is the weight of the barrel, and that is 280 pounds. Okay, so that's the weight of the barrel. Then we're looking at different forces that are here. So weight of the barrel we already have. We're thinking about what's the force that's required to pull. That's my purple line there. And then what else is happening here? What else is happening is we have the actual weight of the barrel against the ramp. Right? So that vector is the weight of the barrel against the ramp. So we're going to need to start labeling these. So I'm going to call that R for ramp. And I'm going to define my variables up here. So R is going to be the weight or the force of the barrel against the ramp. So that's R. I've said out loud what the pink one is, but that's just weight. So let's just call that W. So that'll be the weight with gravity. So right now, this looks kind of disjointed, but let's think about this. So that is a 90-degree angle, right? So the force of the barrel against the ramp is a 90-degree angle, which means also that R is also perpendicular to this force that we're pulling against the barrel. So that is also a 90-degree angle. So if we were to extend that, that is also 90. And what's kind of weird is, as we've talked about vectors, the idea that you can, shift them around to see how they work together. And as long as they have that same direction of magnitude, it works out that they are really the same. So I'm going to take that purple vector and I'm going to move it down here. Okay. Because I want to see how these are interacting together. And for the same reason that that is a 90-degree angle, we're going to put a 90-degree angle right here. Thanks. So if that's 90, then we're working with a triangle that we can deal with, right? But it's seeing those relationships, seeing that, okay, this makes sense that if that is, the force required to keep this from sliding, I can move that down and I can see how it interacts with these other vectors, okay? So let me see what I want to call that. We'll call it S for sliding. All right, so now we have this triangle. We know it's a right triangle because this was perpendicular here, which meant it was also perpendicular if I extended it here. All right, so that's how we knew it was a right angle. So then we also know, this gets a little, you have to think about this here. We also can say that this is a right angle, right? This is a right angle because our force, that is our weight with gravity, was straight down. And this was a horizontal, so we know that that is a 90-degree angle, okay? So if those are 90-degree angles, we know the relationship here. These two angles have to be equal, which means that 12.5 is also that angle. And that, to me, that leap, that takes a little bit with my brain. So that might be true for you too. And I would encourage you, to go back and think through, does it make sense to you how you can come to the conclusion that that's also 12.5? So because these are both right angles, means that these opposite angles have to be equal. And then we can use our 180 really to get the 12.5. So if you can work through all of that, then the rest of it is pretty quick, because what are we actually trying to figure out? It says find the magnitude of the force required to keep it from sliding. So I'm trying to find purple. Can I find the purple vector if I know that angle and that it's a right triangle? Yeah, of course I can, right? If that's my angle, if that's theta, I'm talking about the opposite, right? And I have the hypotenuse. That's just sine. So sine of 12.5. is the magnitude of my vector divided by the 280. Why is it the magnitude of the vector? That's just what I'm calling this side, right? Magnitude of the vector. Opposite over hypotenuse is sine. So magnitude of the vector, if I type it in my calculator, I get approximately 60.6 pounds. All right, I know it's in pounds because it's the same unit as the weight of the barrel. So that is the force required to keep it from sliding. And then it also says find the magnitude of the force of the barrel against the ramp. So force of the barrel against the ramp, I called R, and it's in black. So now we're looking for this side. So now we're going to use cosine. Cosine of 12.5 is the magnitude of that vector R divided by 280. Why is that? Because cosine of the angle is the adjacent over the hypotenuse. I plug that in my calculator and I get 273.4 pounds. And your homework's going to be in Pearson, so just make sure that you look for what they tell you to round to. I went to the tenths here. All right, so creating a picture, really important. If you are labeling a bunch of different vectors, I would suggest labeling what they are, so defining what they are, because I think it'll help you keep it straight. You could tell I defined them and I color-coded them because I feel like that's a lot going on there. But what did we end up seeing? We ended up seeing how it all worked together. How did it work with the incline, with the weight of the barrel? How did gravity play in there? Really interesting to see all of that working together. That barrel might be 280 pounds, but because of the incline, the ramp is only feeling 273 pounds, right? And then the fact that if you wanted to keep it from sliding, even though it's 280 pounds, because of that slight incline, really, it would only actually take 60.6 pounds of force to keep it from sliding. All right. All right, next up, we have our basic two force kind of problem. So you did one like this on the last homework. So where there was just a written explanation and then you tried to do it. So what I want to do is work through this with you to make sure you get the big ideas. And really interesting to see that your book didn't use pictures. You need to use a picture. That is really important to see what's going on, to see what sign you should be using. I would say you really need to use a picture. All right. So magnitude and direction exerted by two tugboats that are towing a ship. We have one that is 4,200 pounds at north 65 degrees east, 3,000 pounds at south 58 degrees east. We want to find the magnitude and direction of the resultant force. So what's really happening to this ship that they're towing? That's what we're looking for. As the two tugboats work together, what's really happening? How are they combined? And what does that effect make on the ship that they're towing? All right. So first step is a picture. So all bearings, we want to think about north and south, right? I actually don't need the east-west. I'm going to get rid of that line. All right, so we have our north-south. Here's the boat that they're working on towing. Okay. The first one goes north 65 degrees east. So north, which is up, turning 65 to the east, if you remember bearings. Hopefully you do. And we're going, that's not straight. 4,200 pounds is the force. And remember in our picture, that looks like the length. All right. So this was 65 degrees. Right. Then it says the other ship is going south, but turning 58 degrees to the east. And that's 3,000 pounds. So there's our 3,000. And that is 58 degrees. And what we want to know is what is the resultant force? What is really happening? And what I want you to think about is when you add these two together, all we're trying to do, the big picture here, is we are trying to write an equation that represents each vector so that we can add them together. That's what we want to do. All we have to do is add them together to see the result of how the two of them work together. And what does it do when we really add them? When we really add them, it puts them end to end. So it says, hey, let me see if it'll let me pull this. It won't. I'll just redraw it. Sorry. So it says, hey, line them up end to end. Right? To see what they're really doing. So if you line them up end to end, what we're finding, what we're looking for, the resultant is going to be this vector. Extend out a little bit. So that's what we're looking for. That's going to be our answer, the resultant. How are the two working together? So when we write the equation, I just want you to have that big picture in mind that when we write each of the equations so that we can add them, this is why we add them, because you are putting them end to end and you're saying, well, how do those two really combine? What really happens to that ship? And that's what's happening. All right. So our job is to create vectors that describe each of these. So here now we do need the horizontal because in vectors we're talking trig. So here's my x-axis. So what I really need, we're going to call this, I'll call this vector 1. You could call it B1 if you wanted to. And this will be vector 2. Right? So to write the equation of vector 1, I have my formula. So the magnitude times the cosine of the angle. Now, it's not 65. It's this angle. So that's where in your book they were subtracting. So 90 minus 65 is the 25 degrees. So cosine of 25, that's my I component. And 4,200 sine of 25 is my J component. I do want to type that in a calculator. It says to the nearest 10th of a degree. So we'll go to the nearest 10th. So vector 1 is going to be 3,806.5 I plus 1,775 J. I went out to two places before, and I'm wondering why. We're going to keep it with the tenths. We'll go tenths. So I'm looking at this. It says magnitude to the nearest pound, direction angle to the nearest tenth. I'm feeling like we should actually probably keep this exact as long as we can. So let's do that. I'm sorry if you're writing this down. We're going to erase that. We're going to leave it just like that until we add them. All right, so let's do vector 2. So vector 2, I'm going to have 3,000 cosine of. All right, so here you're going to have some choices. And what I want you to do is what makes the most sense to you. So here's one choice. 58 degrees we can't use. If you don't want to have to use your brain about the signs, then you can figure out what that angle is. Okay, that angle is 328 degrees. I don't love doing that. I feel like it's a little harder. Let me tell you what I do that makes more sense to me. I find the reference angle. So if this is 58, then this is 32, right? 32 degrees. So what I do is a 32 degrees for both components. And then I see what sign I need to adjust. So I can see this vector, right? This vector is going positive in the X or the I direction, negative in the J. So I'm just going to put a negative out there. If you use the 328, it will make that negative for you. So it's really like, what do you think is easier? Do you think it's easier to have to think about the sines or to have to think about the angles? I think the sines are easier by far for me. So that's the way I like to do it. All right. So what am I doing now to find this resultant? To find the resultant, I am adding these two together. So I went ahead and I kept it exact. So I'm just going to type in 4,200 cosine of 25, 3,000 cosine of 32, adding them together. And I'm going to get that my resultant is 6,350.63 in my I direction. I'm going to do the same thing for the J's, and I'm going to get 185.24 J. That's my resultant vector. So I just found the equation that describes that orange vector. Now for me, I don't like to label the sides there, but I really like to think about what this means. So I'm going to draw myself another little picture and say, okay, so in the I direction, I'm going 6,350.63. In the J direction, I'm going 185.24. So that's my vector. That's the resultant vector. To me, the picture really helps because then the two actual questions, find the magnitude to the nearest pound and the direction angle. Now I know what I'm basing it off of. This picture is what I'm trying to base it off of. So what's the magnitude? The magnitude of that is just Pythagorean theorem. I don't love writing decimals over and over, but that's okay. Here they come. All right, so for the magnitude, and now I'm going to round it, says to the nearest pound. So 6,353 pounds. That is the magnitude of the resultant force. So that's part of my answer. And then last part, we want the direction angle. So now again, because I drew the resultant force that I got, all I'm looking for is this angle, which you can tell is going to be kind of little, very little. So I think the easiest way to find this, I have the opposite and the adjacent, so I'm going to use tangent. Tangent of theta is the opposite over the adjacent. So I'm going to take the inverse tangent of that. There it is. I type that in my calculator. It says to go to the nearest tenth, and I get 1.7 degrees. And that's the answer. So something that came up on the assignment from last class with that last problem, remember, you want to be careful where that angle actually is. So that is 1.7, and you can see that's going up because of my drawing. If you were going in a different direction, you would need to think about what the true angle was. So if I ended up, with something below the axis, what I would need to think about, like that 328 originally, what's the actual angle that would take me there? So you just want to be careful that you end up reflecting what the actual angle is that it would need to be pointing. Okay. What that means, really, like we're avoiding doing a bearing, because another way to write that, if I'm going 1.7, I could say, hey, I'm going north and I'm turning 88.3 degrees to the east. That would be another way to specify where you were going with a bearing. But if it just says the direction angle, you can just use the actual true angle from the x-axis. So just make sure that you put, what you mean.